Good afternoon again. Warm welcome everyone who joined us for today's webinar. My name is Martin Bosak from Barry Transportation, and I will present a topic, Design of Warren Truss Footbridge. It is based on a real project which we developed recently. The outline of today's webinar is presented here. In the first part of the webinar, it will be more theoretical. The points 2 and 3, we will look at some footbridge design specifics and challenges. Also, Eurocode requirements, which are applicable specifically to footbridge design. And in the second part of the webinar, we will look at how these principles and code requirements are implemented in the design and how Midas can help us as designers. A little bit about Barry Transportation, the company I work for. Barry Transportation is an Irish independent engineering consultancy. We focus on 3 main areas, which is traffic management, roads and transportation, and structural bridge engineering. We are covering the whole Ireland because we have offices in Dublin, Cork, and Castlebar, and over 100 employees in the company. And although we are Irish consultancy, the company is well established, over 25 years in business, and also we have many international projects we worked on in Africa, Middle East, and Eastern Europe. But our main project portfolio is in Ireland, and specifically for roads and bridges, Barry Transportation was involved and is involved in the design, construction, supervision, or as a authority supervisory or advisory role for many major road projects in Ireland. A little bit about myself. I have over 15 years experience in structural bridge design. I'm a chartered engineer, and I specialize in concrete bridges, but over the course of my career, I also worked on a number of steel and composite structures. I started my career in Czech Republic, where I worked on a few motorway schemes, also in Slovakia. And after moving to Ireland, I worked a number of infrastructure projects here in Ireland and also in the UK. Well, now let's have a look at what makes footbridge design different from a standard road or rail bridge, and what challenges the designer may have to face when designing a footbridge. I would highlight key points related to footbridge design. It is aesthetics, structural robustness, and need to pay attention to stability and vibration. It is by no means unique to footbridges, but with the footbridge design, we may encounter more often these specific points, and they tend to play a bigger role at practically every footbridge we may design. So if we look at these points more closely, aesthetics, structural design of the footbridge is very often developed in close cooperation with an architect. And architects, they have their own ideas about the appearance, the visual impact of the bridge. Quite often, it's not just the structure, the bridge structure, but it may be some ancillary structures attached to it. It may involve unusual or complicated geometry, so not straight line, but complicated curves, 3D curves, and so on. And also with the footbridge design, it allows for greater selection of materials. So we as designers need to understand the properties and behavior of these materials, even those we do not normally use for road bridges or rail bridges, like timber or aluminium or glass and so on. In terms of structural robustness, when we design footbridges, we want them to be lightweight. Quite often footbridges, they are very slender, airy structures, and at the same time, we have to ensure that they have sufficient stiffness and strength to maintain their stability. It may be an issue for the wind effects, or the critical combinations for the design may be quite different from those we are used to when we design road bridges. With the stability is also related a dynamic response and vibration. It is not really usually an issue for a majority of short and medium span road bridges, but it is an important factor in footbridge design, because if the structure has a low natural frequency, it may lead to unstable lateral response and, in the worst case, loss of stability. But also it may lead to vibration, which may cause discomfort to users. Some of you who visited Northern Ireland would recognize that this is a Carrick-a-Reid bridge suspension footbridge and north coast of Ireland. Now we can have a look at some Eurocode requirements. Just a brief overview of guidance and principles in Eurocode, which are particularly applicable to footbridge design. Footbridges are subjected to different type of live load. So the Eurocode 1, traffic loads on bridges, also contains requirements for dynamic loading on footbridges. Also, accidental actions would be quite critical for footbridge design, as well as wind actions, and some of the clauses in the Eurocode dealing with the wind actions cover the footbridges. The structural design is covered by Eurocode 2 to 6. The same limit state principles apply to footbridges, their global stability, member verification as any other structure. So there wouldn't be any difference in this group of Eurocodes for the structural design. We can have a closer look at the loading, because that's what differentiates the footbridges most from road and rail bridges. The static loads and static load models, they are formed or made up from 4 elementary components, which is UDL, distributed load, concentrated load, then service vehicle, and horizontal forces. And these 4 components, they are combined into groups of loads. It's very similar concept as with the road traffic. So on the footbridges, we either combine UDL and horizontal forces, or service vehicle and horizontal forces, and this group of load is treated as a single live load action for the purpose of combinations and factoring and so on. The accidental loads, they are covered partially in the traffic loading code in 1991-2, partially in the accidental actions, 1991-1-7. Since accidental loads can have fatal consequences for the structure and its users, and strengthening the footbridge to resist the full impact, for example, would be uneconomical. We take measures to avoid them. So collision forces on piers of footbridges, they are reduced because the piers are usually protected by a barrier. Collision forces on decks, we can avoid application of this accident load if we provide sufficient clearance, which is in the UK and Ireland 5.7 meters. And accidental presence of a vehicle on the bridge, again, it can be avoided if a permanent barrier is installed which prevents access of vehicles on the bridge. Now, what differentiates footbridges most from normal road bridges of short and medium span? That's the application of dynamic loads. There are two key points which we need to pay attention to. It's the natural frequency of the structure, because if any of the natural frequencies are identical to frequencies of forces applied to the structure, which would be pedestrians or joggers or cyclists, there is a risk of resonance, which may lead to unacceptable vibration or even loss of stability. So natural frequencies is the first key point. The second key point to pay attention to is the vibration. Vibration from normal pedestrian traffic should not cause discomfort to users. So that's why the code specifies a limit defined as an acceleration limit. Dynamic effects of walking pedestrians can be represented by a periodic force, and this force will have a typical frequency between 1 and 3 Hertz. In the horizontal direction, the effects of walking pedestrians would have a frequency between 0.5 and 1.5 Hertz. And if there are a group of joggers crossing the bridge, that may induce forces with a frequency about 3 Hertz. So we can see that this range, say from 0.5 to 3 Hertz, would be a critical spectrum, and if any of the natural frequencies of the structure is within this spectrum, there is a risk of issues related to the vibration or stability. So specific models and detailed criteria how to fulfill this and how to achieve that the structure is stable. They are defined in national annex or other national application document. And for the UK and Ireland, the Eurocode 1 specifies the maximum vertical deck acceleration, which has a limiting serviceability value in the range between 0.5 and 2 meters per second square. The exact limit value is calculated based on formula in the code, and it depends on the site usage, route redundancy, and structure height. Then the dynamic effects of pedestrians or pedestrian group of pedestrians, they are represented by the application of vertical pulsating force which moves across the span of the bridge. Again, there's an exact formula in the code which helps us as designer to calculate the magnitude of this load. It depends on the natural frequency and other factors. The footbridges, for the purpose of dynamic loading, they are split into 4 classes depending on the location and usage. And then the dynamic loading or dynamic force is applied, different value may be applied depending on the bridge class. Also, we should know that the pedestrian speed crossing, how fast they walk, is also defined, which helps us to define the duration of dynamic loading. The other aspect of dynamic loading would be loading crowded conditions. So if the bridge is located in the city center or close to a stadium, it may get into the crowded state. And then instead of using a point single force pulsating and moving across the bridge, the dynamic loading is modeled by a vertical pulsating distributed load. So the load over area on the bridge. That helps us to assess the possible vibration issues. The other requirement regarding the natural frequencies, it is specified in the code that if there are no significant lateral modes with frequencies below 1.5 Hertz, we may assume that the structure is stable, that there's no risk of lateral instability. If any of the critical frequencies is lower than 1.5 Hertz, then there are additional checks to perform, or we may need to redesign the structures or to introduce some damping devices. Apart from pedestrian or generally traffic loading, in certain situations, we may need to investigate the dynamic effects of wind loading, and the Eurocode dealing with the wind loading also provides general guidance. It says that dynamic magnification effects due to vertical response can be ignored if fundamental frequencies in bending and torsion are greater than 1 Hertz. Or we may need to fulfill alternative condition. But taking into account that generally we want to avoid frequencies below 1.5 or even 3 Hertz, it means that for most bridges where we fulfill the condition for the pedestrian dynamic load, we are fulfilling the condition for the wind loading as well. But for the long span or special structures, it is something which needs to be taken into account. So this was a brief overview of Eurocode requirements, which are applicable to footbridge design, especially in relation to dynamic effects, which are the main point for the footbridge design. Now we discuss how were these requirements applied on a Warren Truss footbridge. This structure has a span of 50 meters, a clear internal width of 3 meters. The maximum structural depth in the midspan was 4.2 meters, and both top and bottom chords of the truss are curved in the gentle radius to improve the appearance. Although in this particular case, the aesthetics wasn't a governing factor for the design because the bridge is in a rural location with low flow of pedestrian. The design of this footbridge was actually developed as a result of a value engineering exercise or value engineering proposal, because the original structure was a 2-span beam and slab, and we proposed a single-span structure to avoid placing the support in the central median of the motorway. and the truss works well for this arrangement. So in the second part of our webinar, we can focus on how this particular structure, or generally truss, can be generated in Midas, how we can generate a model in relation to what we discussed in the Eurocode requirements for dynamic response and natural frequencies. We will look into stability and dynamic response, and again, how this can be performed in Midas. Then global static analysis, member verification, and the generation of the design report. To create the geometry of the structure in Midas, there are a number of options available to us. One method is using Midas Truss wizard. Midas has a set of tools which are called wizards for generating geometry of basic structures. So there are wizards for arches, for culverts or frames, as well as a wizard for truss. We can select specific or the closest similar shape of truss, enter a number of panels, overall dimensions. We can edit nodes or even assign material and sections, and then do the final adjustments when the geometry is generated. So this wizard will generate a 2D truss for the structure, like the Warren Truss footbridge. In our case, this would have to be copied and assembled for a full 3D model. The second method, which is especially useful for larger structures with many elements, or for complicated geometry when we have a skew arrangement or curved structure, we can import CAD file directly, or there's even an option to import or link Midas civil model with a BIM model in Revit structure or Tekla. That's done with the help of an add-on installed in Revit or Tekla, which allows the exchange of information between the two pieces of software. The structure properties, they are standard for any structure. In this particular case, the steel truss is of S355 steel. It's made from the main truss is from circular hollow sections. The rectangular hollow sections, they form the deck cross beams only. And the structure is articulated, sits on elastomeric bearings. So the stiffness of the bearing calculated based on the properties of the elastomers can be again included in the model. There are some additional properties and settings which are specifically related or enabling us to perform dynamic analysis. One of them would be a need to create an element on which we can apply the dynamic force, dynamic pulsating force. In my case, I created a dummy beam in the bridge center line on which the pulsating force is applied. The other important point for the dynamic and modal analysis is setting conversion of self-weight into masses. That's a tick in the structure type setting, convert self-weight into masses. If we want to convert other types of loads, like a superimposed dead load, into masses, that's done in the load menu using the load to masses dialog. The other properties and build-up of the model would be very similar to any other structure. So we define all the load cases and combinations and can analyze the structure. We can now focus on how do we verify or analyze the stability and dynamic response of the structure. I mentioned before that it has two key parts. First is the natural frequency, which in Midas is called eigenvalue analysis. And the other key part is the dynamic response, so application of dynamic load. To investigate the natural frequencies of the structure, we turn the eigenvalue analysis control in the analysis menu in Midas, and we do it by selecting number of frequencies we want to analyze. So in this particular case, I selected 7. We may go for 10 or even more, because some of the higher frequencies still may be realistic and applicable to the structure. Then we need to analyze different modes of vibration, because natural frequency is basically the frequency at which the structure vibrates naturally. And in different directions, in longitudinal, transverse, vertical, or twisting, the structure would vibrate at different frequencies. And we need to prove that the modes of vibration, they are not close to the critical values of vibration induced by pedestrians, which that it's the range of between 1 and 3 Hertz generally. The output from the eigenvalue analysis can be either numerical, like in this example. So for each mode, we can see the actual frequency. So mode 1 has a frequency of 1.68, which is actually close to 1.5 Hertz. But at the same time, when we check what's the shape or what's the mode of that vibration, we notice that it is vibrating in the longitudinal axis of the bridge, so it wouldn't be critical. The second mode has a frequency of 2.53 Hertz. And again, from the table below, we can see that it's vibrating in the y direction, so it is a lateral transverse vibration. And the third mode is over 3 Hertz, 3.47, which is in vertical direction, so actual vertical vibration. So this provides an overview, but we can also check the actual graphic results or see the exact shape of vibration. And on the following short video, you can see how it can be done in Midas. So we go to results, select mode shapes, vibration mode shapes, and then select the relevant mode. We want to display legend, and when we hit apply, it will display the shape of the structure in this particular mode. Also in the legend, we can check the actual frequency and the direction in which the structure vibrates. So here we can see that it's in longitudinal direction. The second mode, yeah, we can see that the shape, deflected shape has changed, as did the frequency. It's exactly the same as in the table showed before. And if we turn on animation and click recording, it will actually show us the shape or the vibration in animation. So we can get a better idea how this mode of natural frequency works. The similar would be for the third mode, which is in the vertical. So it's the classic up and down vibration. So that was the first verification, natural frequencies. For the assessment of dynamic response, we want to prove that the vertical deck acceleration is within the limits set in the code, so that any vibration is not causing any discomfort to the users. How is it applied? Well, we said that the dynamic load is applied by the pulsating or fluctuating force. This in Midas is done the way that the value of the force is calculated in time increments. So we create a set of force values in different defined time, and then the force is applied on a series of nodes along the bridge span. The procedure, how to apply the dynamic load in Midas, is quite not really self-explanatory, but relatively understandable, because in the load menu we have dynamic load type and then series of icons. So basically we follow those icons to create a time history load case, to generate time history function, and then to apply dynamic node loads on the structure if we deal with the node load and not with the crowded condition. In the time history load case, we specify the duration of the load, because dynamic load differs from the static load in the time element. So in this case, the end time in the dialog, it reads 29 something seconds, and it is actually time it takes a pedestrian to cross the bridge, because in the code we have the design speed, or the speed at which pedestrian moves across the bridge. So we know the length of the bridge, 50 meters, so it takes about 30 seconds for the pedestrian to cross the bridge. Then we also specify the damping ratio, and in the time history function, we calculate the value of the fluctuating force for time increments. In this particular case, the time increments were 100th of a second, and the series of values can be copied, calculated, for example, in Excel, and then copied into Midas, which creates this fluctuating force of sine profile. For the Warren-Truss bridge we designed, we applied only walking function, because it's in rural condition and there wasn't requirement for joggers. If we have structure in urban environment, or there's a specific requirement, we may need to create two separate functions for walking and jogging, because they will be different. So this is just a copy from the previous slide of the pulsating force. So this pulsating force actually forms the time history function in Midas. And then this pulsating force, as defined in the time history function, is applied on selected nodes on the structure, as we can see on the screenshots below. We analyze it, and we can review the acceleration or forces or displacement at any point in graphical form or even in numerical form. The problem is, if our time increments are hundreds per second, it's a lot of values, a lot of numbers to review. So it's not very practical to look at it this way. But there's a function in Midas where we can create an envelope of results for any selected point on the structure. And this will create a graph showing acceleration envelope. It's in time history graph function. So this is actually a plot from our Warren Truss footbridge. We can see that the peak acceleration was only 0.036 meters per second square, which is much smaller than limiting value in the code, even to 0.5. And it is because of the low pedestrian loading, because it's in the rural condition, it's category A, so it is not expected to have more than 1 or 2 people on the bridge at the same time. But we can also see that the peak accelerations are close to the middle of the time period. It actually says that the maximum acceleration would be at time 16 seconds, the minimum at 14 seconds. And it makes sense because that's when the pedestrian is right in the middle of the bridge. So it has a greatest effect on the vibration. Again, in the following short demonstration, we can see how to create this time history graph. So we go to results, time history graph, and we define the function we want to create graph for. So we are interested in acceleration. So add new function, create a name for it. Acceleration. We select a node for which we want to create a graph or envelope of results. The greatest movement is expected unless simply supports its structure in the midspan. So we select the midspan node. We want get accelerations in the vertical direction. And we use it for the load case we created for the dynamic load case. We can even select which mode is critical for this. We will be the mode number 3. So this will create a function for graphing. And then we just select the function. It either be added on to the list, or in this case, it is already on the list. We create a title for the graph. So we are creating acceleration envelope and then hit the graph, and the graph is created. If we want to present the graph further, export it, or use it in the report, there's a button next to the graph, which is dynamic report chart. And it basically creates a reference of this graph, which we can use for the creation of the report. So this was all related to dynamic analysis, investigation of natural frequencies, and vibration of the structure. The global static analysis is performed the same way as any other structure. We generally look at 4 main types of results, which are deformations, reactions, stress results, and force diagrams. Deformation, we tend to take for granted that it's so easy to get all these results from the software, but it's good and prudent to review the deformation as a first step after the analysis, just to verify that the model behaves correctly, that the deformations are realistic. It can also help us to see if there's a need, particularly for the steel structures, to introduce any precumber to compensate for the sagging from the permanent load. And we also verified that the deflection of the structure is within the limit given in the code. Similarly, the support reactions, yeah, we generally want to use them for the bearing design to create a bearing schedule and pass them to the bearing designer. But as a first step, we should review the model results and compare them with hand calculations. So to have idea what magnitude of reactions we should expect for permanent loads and live loads. And especially with statically indeterminate structures, we may check for any anomalies, any high reactions, any particle direction or moments, and so on. And both graphical and tabular output, as presented on this slide, can be inserted into dynamic report. For a steel truss like this one, an initial member sizing is based on a global stress in main chords and the most stressed diagonals, which are near supports. So again, this is something to help us with the initial design. And review of bending moment diagram. It may not seem important for a truss where we have we expect mostly axial forces, but if the structure is modeled like this particular one as a frame instead of using truss, tension, compression only members, then we need to verify that there are no higher or high bending moments in connections, which would affect the member verification. The member verification is the final set of checks, and it is usually the most time consuming because there's a number of hand calculations we need to perform. They are highly repetitive. For each critical member, we need to perform a same set of calculations. Quite often in the office, we have in-house prepared design spreadsheets which save time, but we still need to identify which members are critical. We need to transfer the results from the model and put them into the spreadsheet. So it's quite useful that Midas has a set of member design features which simplify this task. And the member design or member verification in Midas has a kind of a 3 layers or 3 levels. The first layer is the overview of member checks. So in the design menu, in the steel, we have a code check option, and this table provides a very clear overview whether all elements are passing the check, what's the sectional utilization, and also the design effects, the forces which were taken into account, and the resistances. So this is the first layer. The second layer, if we select a specific member from the table, we can display graphic results, which provide more details, some design parameters, checking results. And again, we can export this or print it out. And the third layer is the text output. Again, we can select a specific member and get text output with detailed description of loads, properties, and verifications, which is typically several pages of text, but very detailed and closely following the structure as required in the Eurocode. So this helps to simplify the member verification, taking into account the imperfections and so on. Then the last part of this webinar, I will talk just a few minutes about dynamic report generation. We need to record our design process as designers for archiving. We may need to provide the information to the design checker. If we collaborate with other designers, other structures, we may have to pass the information on. And sometimes we want to present the results of our analysis and design. So for all these reasons, the dynamic report feature in Midas, it provides an effective means how to prepare such report. Dynamic report, the idea or how it works is that we create a model references which we want to include in the report. So it may be graphics, images, or screenshots of stresses, reactions, bending moments, and so on. We can also select some tables and charts, like the acceleration chart we have shown before. Then we start the dynamic report generator and insert those references into the report. We may add our own notes or additional information, save it, and if anything in the model changes in the future, we need to update load values or update the structural arrangement. We can always open the existing report and update the information from the current model. So I have a short video here how this can be achieved in just a few minutes. So we go to Report tab in the tree menu. We can select the basic formatting, font and sizes. We can select the information we want to include in the header and footer of the document. And then in the tools menu, there's a dynamic report generator. So when we create a new document, it opens basically a blank Word document within the Midas. We can add header and footer we prepared, and then adding information from our model. So there are groups of information: images, tables, charts, and text. And some of them are predefined, prepared automatically. Some of them we need to select ourselves. So we can include the structural view of the model. We can insert the control data of our Midas model, or list of our static load cases. When we analyze the natural frequencies, we may want to include some of the illustrations or figures of the critical frequencies and their shapes, as well as the table providing the information about all natural frequencies and their direction. We also covered the acceleration. So when we create an acceleration graph, it can be inserted into the dynamic model, dynamic report. And from the member verification, the table with the overview of member verification results, again, it can be inserted into the report, providing the overview of the member checks. So then We can add our own information, explanation, or notes and save the report as we would do with any other Word document. If we want to update the report, again, we go to Tools, Dynamic Report Generator, and instead of creating new document, we select Open Document. So we select the report we created before. The report opens. And then another menu, Dynamic Report Auto Regeneration, is highlighted. So we can actually select information we already have in the report, like images, tables, or charts, and tick boxes which of them we want to regenerate or update with the most current values from the report. So the benefits of dynamic report are obvious. They allow us to select various types of information from the model views, diagrams, charts, tables, or even text. And because the report is linked with the model, we can make sure that it will be always up to date. The fact that it is generated in a separate file in the Word document, it also opens to us a possibility to add additional information and modify it, format it as we wish. And the report can be updated to reflect any model changes. So this brings us to the end of the webinar. I hope that you found it beneficial, that you learned something maybe from the dynamic analysis and the specific points related to the Footbridge design, or some of the tools available in the Midas, which can help us in the process of the analysis and the design of Footbridges. So if you have any questions, you can type them into your chat window, and in the next few minutes which we have left, I can try to answer some of them. So the first question here was, in order to understand the dominant direction for each mode in X, Y, or Z in eigenvalue analysis, shouldn't you check the participation mass percentage instead of the displacement? Sometimes it's tricky trying to figure it out from the displacement only. Yes, although I showed it as an example how the second part of the eigenvalue analysis results can be useful. I tend to always check the mode of vibration or the direction of vibration from the graphical results, because it's the most clear. The second question, when calculating the design acceleration limit, does the factor K3 related to the overall depth of the structure? Possibly. I would check the exact wording or explanation in the Eurocode. but it makes sense that that it is related to the depth. But yeah, I would need to check it from the code itself. Interesting question. How does Midas check the top chord capacity with no buckling analysis performed in order to find accurate alpha critical values? That would be done as part of member verification. So in the member verification, in the design menu, when we do the member verification, we can introduce or specify the buckling length of the element, and then the member is verified using or taking into account the local imperfections and the actual length. So we wouldn't get this answer from the global static analysis, but in the member verification, this is included, the buckling strength. Yeah, again, the buckling checks, they are part of the member verification, and if the buckling length or the actual distance between connections corresponds to the member length, it's taken into account automatically. If we have any intermediate nodes in this structure or in the chord, then we need to specify manually what would be the actual length of the element for the purpose of buckling. Interesting question. Do we need to check the combined dynamic effects, pedestrian and wind, or individually? If we need to include the dynamic effects of the wind, then I would expect to do a combined check. But as I mentioned, for most normal structures or footbridges of short and medium span, we're not required to include dynamic effects of wind. So then we would do just the pedestrian. Another question, was there ever a need to modify or update the model during the design process? In our case, there was a slight modification. Initially, we proposed to use square hollow sections, and after the comments or requirement from the client, they were changed to the circle hollow sections. So, but that was relatively minor change. Of course, as an example here, height of truss, would you have benefited from a parametric tool such as Grasshopper Dynamo? I can imagine there are structures which benefit from such tools. For a truss like this particular one, I'd say it would be probably an overkill to do a parametric modeling. When a structure is found to be unstable in the lateral direction, is there a generally agreed upon model for the lateral pedestrian force? Eurocode does not give a load model for this case. The Eurocode provides a guidance that if the structure is laterally unstable, then we should look into changing the structural arrangement, so increasing the natural frequency, or introducing, for example, a damping devices. So I wouldn't say it's a matter of changing the load, but rather changing the structural arrangement. Maybe the last question, because we are over time now. Are additional checks required for U-frames, end frames, top chord effective length, and girder restraint? Were there any splices in the top chords, and how were these formed? In this case, the truss was braced at the top, and there was a full diagonal bracing at the top. So the effective length was given. The structure was fabricated in 3 parts and delivered on site in pieces, and then welded. So the splices were full penetration butt welds basically. So it didn't affect the design as such. Well, there are quite a few other questions, but perhaps I would thank everybody for your questions, also your attention. If you want to raise any further questions, you can contact the technical support of Midas as shown on the last slide, either tech support at Midas IT or UK support. You can also check the support website, which has a vast information available regarding the modeling and also technical things. And I may review the questions I didn't manage to answer and get back to you maybe directly. So thank you again, and goodbye.